Just to get a quick check, was everybody there tomorrow, or the people who just joined us? Like, it's important because I know the session have been advertised. I kind of separate, but no, like what I've done this morning, I want to just make sure that it's all set, and then we'll move to one of the techniques to do computations. Before we start, I want to make sure about like this computer lab tomorrow. So there is this software that's called RepLab. So you can obtain the software using two kinds of instructions. Either you look at what's behind the program, and then it will give you like a URL GitHub RepLab. But then it tells you to download something using this clone or download button. If you do that, parts of the project will be missing because these are things that come from other people. So what I've done below, you have a link to a zip file over there. RepLab 0.4.1 full. Or you just use the link that you received by email, but make sure that you don't download using this link here because parts will be missing. You need to use Git to retrieve them. It's a bit complicated. So when you click on the link, whether it's the one you received through by email or the one that's over there. Okay, the Wi-Fi is a bit sometimes tricky. Anyway, I won't maybe if I switch to the, okay, it doesn't want. Anyway, you will go to a Dropbox page that I can't show you right now. What you do on the top right, there will be a download link. So whatever means you go to the Dropbox shared link, you need not to explore the files, but you want to download the, yeah, okay, it appeared. So you want to click on this download here and direct download. Then you will get the zip file. Here I already did it before, so I can just stop that. You get a zip file on your download folder. You extract the zip file. I can replace everything. Then you get this RepLab lab folder. Then what I'm going to do is I'm going to open MATLAB. I'm going there, and I'm going to show you the instructions so that you can make sure that this is running on your computer. If it's not running, if you can't make it work tonight, I'll be there until like the end of the sessions. I will still be here tomorrow before the lab, so we can solve the problem during breaks. So now I need to go to the folder that I've just extracted. It's over there, so I'm here. The first thing I need to do, it's all written in the instruction sheet. You need to add the path for all the other packages that I'm using. There is a command to compile something that you need to run if it's not compiled already for your computer. So I'm just doing that. Normally it should work like immediately. And then there is a command you run, you type. Everything again is in the instruction what you need to type. You run it. What it's going to do is to run all the tests to check that every function in the software is functioning properly on your computer. If anything here, like it's written like failure, and if the failure that we have at the end is not 0, then ask us. Just waiting like 1 minute for this to finish. Some people during the break ask me, okay, I don't know to use MATLAB. I'm starting to learn C. Do I need to know the program to do the tutorial? The answer is no. Part of it will be pen and paper. Part of it will be on the computer. And then if you know the program, you know the topic, I'm happy to like push you way forward. But this will be like an introductory session. So it can be a bit slow. So yeah, okay, we are near the end. Yeah. So what you want here is the answer is 1 and okay passed 601 and no failures, which we don't have failures over there. Good, so I'm leaving MATLAB for today because we are not going to do much at the beginning of this session. Before I go back to a whiteboard thing, I want to show you this. So this relates back to the triangle. Okay, the problem is that I don't have much contrasts. I think I can turn on the lights, right? Like which switch should I push? Yeah. Those ones here? Okay, good. And I think we have enough contrast to see both. And you don't need to read the stuff there. What I just want to give you is an impression of how much we don't know there. Actually, to see the green stuff, maybe I'll need to turn the light back later. So this morning, the big question was, how do we characterize the correlation P ABC, where ABC are bits, so we have 8 coefficients. Wait a minute. 1, 2, 3, yeah. No. So we have this vector like of these 8 coefficients, and we want to characterize which one can come from a structure that looks like this. And we have seen, for example, that there is one point. It's the point that I call equal, which is basically 1 over 1 half 0, 0, 0, 0, 0, 1 half, perfectly correlated. This point is not in the set, in this triangle compatible set. But for the other points, we don't know. I'm going to tell you in a minute, like, how could we plot this? One problem that we are going to have is that this vector here has 8 dimensions. So it's not something I can readily plot, something in 8 dimensions. Luckily, we are going to use a trick. And the trick is this. We are going to add a restriction to our study. What we're going to say is that we study models where the correlation are symmetric, where P ABC, when the so ABC is going to be IJK, it's equal to JKI, so I can do like cyclic permutation of my correlation, they say the same, and it's equal as well to, it's sufficient that I just permute the first 2, and with like a cycle permutation and just a transposition, I have full symmetry. So now what's going to happen is that we only have 4 distinct coefficients in this list. So the 0, 0, 0 stay the same, stay invariant, 1, 1, 1 will stay invariant. And then this block here will take the same value because I have added this restriction. And the coefficient there take the same value in gray. So I need now 4 degrees of freedom to characterize that. But then I know that if I do the sum of all these coefficients, that sum is equal to 1. So what I'm going to do, I'm just checking with the figure which one I removed. I'm basically just forgetting about the green because I don't need to plot it because I can always recover from the other ones. So now I'm going to give an axis to each of those values. Just checking. So this one is going to be the x-axis in my plot. This one is going to be the y-axis, and the weight of the blue one is going to be the z-axis, like the one that goes kind of inside the screen. So now we can do a 3D plot. And of course, what we have is this condition that I will put in red because it's in red in the figure. The condition is that 1, okay, I think everybody can read if I kind of hash it like that. 0, 0 minus P111 minus 3P001. So this should, because this is equal to, and this divided by 3 is equal to the missing 1 by normalization, this should be also non-negative in red. So let's look now at this graph. And then later on, when you move to the right, I'll turn off the light. So now, right now you can see at both things, and then later on just at this screen. So x-axis goes from 0 to 1 because that's the weight of a laptop don't go to sleep. Thank you. Okay. So I need to wiggle this mouse every now and then, which is going to be a fun game. If I forget to do it, it will turn off again. So what do we have? X-axis goes from 0 to 1 because that's the probability of 0, 0, 0. So we go from 0 to 1, and like the point that has here a coefficient 1, it's the point that where everybody always outputs a 0 because it has probability of the 0, 0, 0 equal to 1. y-axis is the probability of outputting 1, 1, 1. So the range is also 0 to 1. And the point that's over there on top, it's that point where they always output 1. So now you can think what will happen if I'm basically in the middle is the point where the probability of having 0, 0, 0 is 1/2, and the probability of having 1, 1, 1 is 1/2. So you can see like this is like 0.5, and this would be like 0.5. It's kind of a 3D plot. And we know that that point is forbidden. So that's interesting. When they all output 0, it's something you can always do. You don't even need to have shared randomness or locally done variable to use that information. You just say always output 0 or always output 1. These two you can do. The one that's in the middle, we can't. So it means that the shape of the set that we can do actually is going to be non-convex. It's going to be some kind of banana. The last axis, okay, here I said y, so I just need to correct that. I did not see that I changed that convention. So this is y, and this is z. Story stays the same. I just want, if you write down anything, that it's internally consistent, not that tomorrow you look back at the notes like what's going on. It's already complicated enough. Now that y-axis here, it's the probability of having 0, 0, 1 or 0, 1, 0, 1, 1, 0, 1, 0, 0. And this one, because it appears 3 times in the vector, it can't go all the way up to 1. It has to stay between 0 and 1/3, because we'll have these 3 components that appear. So we go from 0 to 1/3. What's interesting is that if you go all the way to 1/3 in this one, you get the vector where one of the parties output 1 and the other two say 0. And that vector, of course, can't have the coefficient for 0, 0, 0. The other coefficient has to be 0, because if you have 1/3 there, you already saturate the normalization. So there will be a point behind there that's going this point where you have only one of the parties outputting 1 always. So this is the situation. And we wanted to do some plots, like to kind of guess what this shape would be. So the idea is it's actually quite difficult to find ways to bound that set. So we use a different way to solve the problem, like heuristics. What we did was to generate models at random. So we fixed the dimension of the shared randomness, maybe 2, maybe 3. We used small values because they work better. And we generated like 10,000, 20,000 points. And we made sure that we generated a model that was symmetric. So we obeyed the condition for the plot. And all the blue points that you see, they represent things that you can do with models that respect that causal structure. What we did, like the red plots, like on the back, top, bottom, they basically represent projections, like if you had a shadow of those points. For example, if I take the shadow over here, I see that I can do the point that's everybody outputs 1. I can do the point where everybody outputs 0. And in between, I kind of stay very low. I never go to the point that's forbidden, that we proved, or that we prove later, like this half and half perfectly correlated. This seems forbidden. Okay, so we have this shape. Interestingly, remember we had also this point where they never output 0, 0, they never output 1, 1, 1, that everything else is equiprobable. So what that means is that this axis will be 0, this axis will be 0, and on the axis of having just a single one, I will not go all the way up to 1/3, I will go to 1/6. So that the missing thing is also 1/6. And it's this point over there. And we see that it's close to the samples, but it's actually a point that's very difficult to go just randomly. You need to have a lot of structure in your model. So this is why it's a bit outside. So now we have this question. We know kind of everything that stays close to the shape, probably you will find a model because it's very close to existing models. But things that are outside, it's maybe models that have a lot of structure that you will not find easily using random techniques, or maybe it's impossible. How do you know? So now I think I'm done with this. I will turn off the light. I just want you to be able to see that green, which is not. So let's see what we can do just with those. Okay, on this side. Good. crap. It's not very good. Eh? I should have checked that earlier. Probably the gamma value. Okay, but I think I hope everybody can see the small awkward lines on those graphs. Is anybody who's like it's all white? Okay. God. Okay. Can I do anything here? No, I don't think so. So what I will do, I will use my mouse and I will. You mean the?
Reducing brightness.
Yes, on the projector, but it's probably going to take too much time to do that. Or can we do it? I don't have like the control. Oh, good idea. Can I do that? Oh, great. For the solved. Thank you. That's awesome. So, so here it's what we have done is to do cuts of the correlation for different part of that figure. Let me just get back to it. So what we've done is to do cuts at z equals 0 on the very bottom, like this, then on 1/8, and then on 1/2. And we plot what happens. The pink things that you see, that were green before, they are inequalities that were derived using the inflation technique. So you see that you have all these, like they are very messy. They look very messy. Actually, they are quite simple polynomials. It's just that when we plot them, we get a lot of things. But now what we have here that was white before is the part that's allowed by those inequalities. So this p equal that we checked at the first session this morning, actually it's far away from the allowed part of the set. So we know that we can definitely rule this one, but we can also rule out points that are close to it, which is great. The thing is that if you do an experiment, you don't want to just prove impossibility for points. When you do the experiment, you will have a bit of noise, so you want to have a bit of buffer. And the farther away you can find a point that you can test, and it's incompatible with the theory, and the more you have that's ruled out by inequalities, the happier you are, and the happier people doing the experiment are, because they can actually be there because they have noise, and it's still okay, you still demonstrate your points. I'm going to go a little bit below. The thing here, we barely have samples, so we don't know what happens with this part of the set. If I go a bit down, P random is the one completely random, like the distribution where every answer is equiprobable, like everything has probability 1/8. So it's definitely in the middle of the samples. And we have this little bubble of samples, but all around there, we don't know if it's allowed or if we're not imaginative enough for sampling. And the same, like that's at the very bottom of the graph. We have a few samples here, but this part, like in this part here is completely disallowed, but in between we actually don't know. So you see that it's a problem with like 3 bits of outputs, something that I can explain like in an hour in a lecture, like state the problem. But to solve it, we don't have a good technique. Something what I will show you now is a technique that works in principle, that normally would describe that set, but if you really want to describe that set precisely, you need basically the computing power of the universe. And if you stop midway, then you get some approximation of the set, like we get here. And those approximations, they will get better and better, but I don't think with that method we will have a direct answer. So that was here for this graph. I think it was a good idea to, in the middle of the session, just have something a bit more visual to see what we are dealing with. I'm happy to take questions on that now. Otherwise, I mean, we will like turn on the light. I close the computer for now, and we will move to like the whiteboard thing. So last call before I close this. If there are no questions, then let's put back the lights. Cool. And I guess I have to put this up. And then I can close this laptop for now. This night mode is amazing. If I have the gamma problem again, so it's really cool. So now the program for this session is that I will revisit the proof, the very last thing we did this morning that was really rushed, so we'll take more time to unpack it. Then I'll discuss the case quantum versus classical with this inflation business. And then we move to the sum of square techniques. And with the sum of square, we solve a problem that's like more quantum in nature. It's the compute the quantum bound on the CHSH inequality. And actually, I'm very happy that Amin presented the quantum measurement because that removes part of what I have to tell you. Anyway, let's restart with the correlation that we want to test. Let me see, I think I had one that was thicker. Probably, yeah, this one. Yeah, this one is a better tip. So the P equal ABC, I don't write the name of the random variable below because we can always take them from the indices here. And this was 1/2 if the output A equal B equals C and 0 otherwise. And now we want to prove that this is impossible using a causal structure that like this one that I will call the triangle structure because we have one variable here, one hidden variable there, and one last variable there. So the question is what we observe triangle compatible or triangle incompatible? Just before we finish, I start with the proof. I had a question or a remark doing just before lunch about like a causal explanation or like observing correlations. And what's really important is that this is observed data, and this triangle it's a model. The only thing that we will be able to do with those techniques is to check compatibility. So we are going to go to the proof, or later on I'll show you how to run a program to do that, or like something you can compute with when it gets more complicated. The only answer that we are going to have is compatibility no or yes. And actually the interesting answer is the no, because in that case, it means we have falsified this model. It means those correlations can't come from this model, which is a valuable piece of information. For example, in a purely classical world, when we see this correlation is incompatible with this, it means I require a structure that's more complicated than just information shared between two parties. I need something to share information between three parties. So now I've deduced something. I need something in common for the three parties. When you move to quantum, which I'm not going to do during the tutorial, but the same question you can ask for quantum and entanglements. Do you only need a quantum state that's produced between AB, BC, AC separately? Or do you really need a state to produce those correlations that's between the three parties? So people will use that to test like the claim that I have real entanglement between three subsystems, and then you check. Maybe you say, no, wait a minute. It's actually compatible with like a structure where you only have entanglement between two parties. So your claim is crap, like I disregard it. You can do those tests with this. But here we stay with the classical world anyway. But when you get a yes, it's compatible, it doesn't mean you have a causal explanation. And that's very important. Because there may be other models that fit your data as well. And then you have no way to say what is the true model. Somebody recommended the book by Julia Pearl, The Book of Why. I was not thinking of putting it in the references because I have yet to read it. But my colleagues at Perimeter love that book. So I know there are people in the audience that love that book. So it's a clear recommendation, but I don't know yet what's inside. So that being said, inflation technique, we'll set it up again. Another remark I got to this morning is that there is glare on this whiteboard, and depending where I write, it can be difficult to read. I'll try to write things bigger, but you stop me and you tell me if it's kind of unreadable, like anywhere you sit in the room, because from there I can't really say. So original scenario is going to be the scenario we test. It's this one. And I'm going to be a bit lazy. I'm not going to do like 2 arrows and a circle and so on. I'm just simplifying that. I put like a double arrow. It means like circle and going there, just to simplify a little bit the visual. Or AB, that's gamma over there. beta over here, alpha here. So that's what we consider. And all these players, they output a bit. So now what I'm going to say is that if I have a device, 3 devices here and here, 3 sources of those local variable, those hidden variables that go to these boxes, I can take the setup and rearrange things, which is what I'm going to do. And what I'm going to do is I'm going to put Alice here, but it's a different Alice from the one there. The output will be different, which is what I put A1, I have a B1 there, a C1. So what these boxes do, they do the same processing as before, but the sources will produce the same thing as before, but I will do the connection a bit differently, so that what I will observe there is slightly different from what I have here. And because I have made the change, I will be able to draw a conclusion, which is a great thing about inflation. So between A and B, I now have gamma 1. Between B and C, I now have like just like the same device as I had before. But now I'm making a small change. On the right, I put beta 2. On the left, I put beta 1. And I mean, it was a source that produced variable going to the copies of the variable going to the 2 boxes. So here I have, of course, a dangling wire that I just put to the trash. And here the same thing. So if I had an experiment in the lab and this was a source of photons and measurement devices that receive 2 photons, I could still make this experiment work because I'm plugging cables that have exactly the same connection as before. So that's something I'm saying it's physical to make that modification. But of course, because I wired things differently, I can't expect that I get the same observation. But actually what will happen is that if I look at this part over there, and I look at the part of this graph over here, apart from the label, beta 1, alpha 1, gamma 1, apart from these labels, the graph is exactly the same. Because what happens in an experiment, if you have like wires going out and you don't receive influence from external things, whatever you send to other system, if you just forget what happens to them, it's not going to change your observations here and now. So otherwise you would have problem with the cause and effect, that if you could be influenced by things that are out of your lab. So if I stay in this bubble and I forget about C1, and if I take my original setup and I forget about C, what I will observe is that I get exactly the same probability distribution as an output. So now I will write this constraint on the board. So with the blue graph or subgraph, what I get is this. P of my original setup, AB, here I put in the indices because I will relate the 2 graphs. It's equal to P A1 B1 of IJ. First condition. And of course, what's P AB of IJ? This is the sum over C of P ABC IJC. It's the marginal distribution. One thing, I don't hear myself in the loudspeaker anymore. Do you still hear my voice? Okay, good. Only some people. So that's the first condition I write. Now, I don't know what should I do. Should I use exactly the same graph? It starts to be a bit busy. Maybe I will draw it again. So maybe here. Okay, while this happened, I was looking for the pen that was a bit larger. Yeah, this one is better. I'll use this one. So the distribution we test, I put it again here. Probability is 1/2 if A equal B equal C, and 0 otherwise. So now I'm going to repeat the argument that I've done there, but using different parties. Gamma, and here beta, and here alpha. And the subgraph that I'm going to look at is the one Now that goes on the right. So what I'm doing here, taking the green pen, and I'm taking this subgraph there. And on my graph here, I will do the same. I take this subgraph over there. And now what you see is that both these graphs, they look the same. So now I can go on my board over here and say that P, this one is slightly used, so it has a better grip. Pij is equal to P BC is going to be P B1 C1. Maybe I'll just use J and K because that's better not to repeat indices. And C1. And of course, the one on the left is going to be the sum over A of P A B C A J K. And the one on the right, I did not write. This one is going to be the sum over C1 of P A1 B1 C1 of I J C1. And the same thing here on the right, sum over C1 A1 of P A1 B1 C1 A1 J K. New constraint, the green constraint. I always play this game like where did I put my pen? So here's the same one. Now I'll do a last constraint. I'll reuse this graph because now we start to be a bit like warmed up over those things. So you have A1, B1, C1. Okay, C1. And what I'll do, so on this graph I've done observation where I removed A, I removed C1. Now what happens if I remove B1? So if you take notes, you can just cross it, what I'm going to do, because it's going to be even clearer. I'm just going to erase it. Nothing here. So what happens now is that that graph is completely disconnected between A1 and C1. So the conclusion that I'm going to arrive at is that PA1 C1 is a product distribution, so a bit the same spirit of what we have seen this morning. If you have variables that you observe and they are not connected in any way, then they will have no causes in common and they will be independent. But now the cool thing is that I could not relate A1, C1 to something that was on that graph before. But now because I've made a split here that I retrieve here, then now I can match this and this independently with the original graph. So A1 just alone corresponds to this. And C1 alone corresponds to this. I'm not going to just overload the graph, like it's enough to see how it works for A and then C is the same stuff. So I can say now that, I'll add it on the board over here with a red dot. Now I have that P A1 C1 of IK, it's equal to P A I P C K. Okay. Drink a bit of tea and then I'll go for the punchline. Whew. So let's have a look at what we have here. PAB of IJ, and on the right I have PA1, B1. What do I know about those things? PA1, B1, it's a scenario that I made up, so I know nothing about it. But PAB, it actually comes from the distribution I want to test. So now my question for you is, what do we know about PAB? What's its distribution? So if I write like PAB of AB for AB 00, 01, 10, 11, and the probability will be on the right. What coefficient do I put there? Yeah. So for 0, 0, and 1, 1, you want to put 1 over 6? And for the rest? And 1 over 3 here? Who agrees with this? Just remember the distribution we test is this one. Actually, it's a test to see if everybody is woken up after the tea and the stuff. So let's do the computation, and I'll remove this guy over there. I have it here. So let's just check. For example, I compute PAB of 0, 0. It's going to be the sum of the values of C, of PABC, 0, 0, C, and C can take the value 0, 1. So this is going to be PABC of 0, 0, 0 plus PABC 0, 0, 1. And the value of, okay, maybe I should have this guy. What I will do is maybe reuse that part and remove like the comments that relate to a figure that's no longer there. And the symmetry doesn't have to be there anymore. Neither this condition. So, okay, what are the coefficients that we have? P 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. P. And because here I have 1/2 for the first one, then 0, 0, 0, 0, 0, 0, 1/2. Then this one is going to be a half because this is 1. And then the values I'm going to put there is for this one, I have 1/2. 0, 1, 1, 0, there are coefficients where I have nothing here. So they will be 0. And the case for 1, 1, I sum 1, 1, 0 and 1, 1, 1. It's going to be 1/2 again. The last thing I will need, like another thing I will need, is PA of A, and it's going to be for A equals 0, 1. The value P is going to be 1/2 and 1/2. So then it means that if I take PA, A, and PC, C, I'm going to get for AC, crap, nobody can read there anymore, right? So I need to cram it. So if I do the product, the answer is that the 4 cases 0, 0, 0, 1, 1, 0, 1, 1, they are all equiparable with probability 1/4, because I just multiply, like I take the product of this twice. So now we have most of our ingredients. So because what we are looking at here, we are going to say, hey, wait a minute. I know this value, I know this value, I know this value. In particular, this one, we just computed it. It's 1/4. This value here, it's 1/2 delta function jk, like j equal k. And this one is also 1/2 delta function ij. And then our big question in this scenario, we are going to ask.
Sorry, how does the last one work? Is it
Wait, because A1, C1. Here, when we remove B, now it becomes disjoint.
Yeah.
So that thing relates to A alone, which is 1/2, 1/2. Mm-hmm. That thing relates to C alone, which is 1/2, 1/2. And now they're independent. I can have the thing. By the way, thanks for the question about like the remark about like the ones, like when we try the 1/3, 1/6. That was a really good answer because I think it's really important that we unpack and check what we compute right now. The question that we have is, does this exist a distribution P A1 C1 B C1? That distribution needs to have every coefficient greater than or equal than 0, and we need to have normalization. And once we have that, actually here I could use like the real indices. So this sums to 1. One thing that I will not dwell too much into, but what we have on this board here is a linear program. For those of you who are interested, there will be an exercise tomorrow in the lab. A linear program is an optimization problem where you have a certain number of decision variables, those ones, we have 8 of them, and all the constraints that you apply, they are linear. And sometimes you maximize an objective that's linear as well. Sometimes you just ask for feasibility. This is actually here we have a feasibility problem. And these are problems that the computer can solve, not exactly, but you get always an answer that's supposed to be correct up to numerical precision. That differs from optimization in general, where you get an answer, but you don't know if the computer has looked hard enough. Those problems, they are convex, which means that what you get is always the global, like the correct optimum up to a numerical precision. So like those equations, those are the ones you would put in Mathematica or MATLAB or your favorite package. But here we have something great, that we can do logical deduction on that problem, which means we can do it with pen and paper. So let me try to do it. With this condition, we know that B1, C1, it's a delta function. So it means that the output there and the output there, B1 has to be equal to C1. Because they have to match these probabilities where the value of the variable are always equal. With the blue thing, we know that always we have A1 equal to B1. So now we put those two conditions together. What do we conclude? A1 is equal to C1, always. But then we have this last condition here. And from the matching that we did, we know that this is 1/4. So it means that this distribution A1, C1 has basically all solutions 0, 0, 0, 1, 1, 0, 1, 1 equiprobable, which means that we have a non-zero probability of having, from that, we know that the probability of A1's not equal C1, it's actually 1/2. That's another condition. And we have this, we also have that conclusion here. These two, they contradict each other. So we have a logical inconsistency in our model. So what do we do with this? Now we go to the final thing. What we did was to assume that P equal was inside the set of triangle compatible correlations. That was our assumption. From this, we assumed that there existed a model. So that means variables alpha, beta, gamma with a distribution P alpha, P gamma. And we assumed that they were that the boxes could do some processing described by probability distribution PA to PC. Remember, we have the PA of A given beta gamma. We assume that all these things existed. And if this model exists, then we can move those things around. And now it means that there exists a model for the inflation. So that's what we assumed. And then we looked at all the consequences, what we could derive for this inflation model. And then we arrived at an impossibility, contradiction. So now in logic, we have something. I don't have much space over there, I'm just using that. That if I have a proposition X, and I know that X should imply Y, but now I prove that I don't have Y, then it means that I don't have X either. Because anytime I have X, I have Y. If I don't have Y, then it means I can't have the thing that comes before. So now we do exactly this. We don't have the inflation model is not compatible. So that means this is not true. So we just prove that a P equal is not part of the set that we are looking for. Whew. That was cool to do this in detail. Just a question in terms of timing, how much time do I have left?
35 minutes.
35 minutes, that's perfect. So now let's take like a few minutes question and answers on that thing. What I wanted to tell you next is what the difference between quantum and classical for those problems, and then we'll move to sum of squares where I'll sketch a brief introduction to sum of squares. Are there questions of what we just did? Yeah.
Can you talk about what properties the map between the triangle model and the stated model?
Okay.
What properties they share and how they
Okay. I think that's a really good question. So in this, I assume that there was a model there. So here, I assume that there exists a distribution of alpha, a distribution of beta, a distribution of gamma, and there exists also processing function for A, B, and C. So these will be my ingredients. When I say that there exists, actually sometimes when you have correlations that are compatible, this solution is not unique. So sometimes you have like different ways of representing exactly the same correlations. But I don't care. I mean, like, if there exists any model there, then in the inflation that I created here, I will say that I have exactly the same processing, but now I just connect the graph differently. So what they share is that they use exactly the same processing, the same distribution for variables. What they don't share is that the variable can be linked, like the causes and effects can be linked in different, like with a different topology. There is just one restriction. Gamma 1 connects A and B. Gamma here connects A and B. You can't connect things that are not compatible. So for example, I could not say, oh, here instead of gamma, I'm going to use beta again. I can't do that because in the model, I did not assume anything about the type of the variable, the cardinality. Maybe actually the model would be alpha is a bit and gamma is 2 bits. So of course I can't substitute things, it will not work. As long as I write an inflation that's compatible in the sense that I connect the same things, but with a different general topology, it will work. Yeah?
I want to ask that why the variables A and C are independent.
Oh, why A and C are independent here, you mean?
Yeah, because the contradiction is arising from this.
Yes, yes.
Why are they-
So the thing in that graph, the original one, if I remove B, A and C are still connected. So in the original graph, when I look at PAC, by symmetry, it's going to be the same values as here. I will have this 1 half, 0, 0, 1 half. Now I'm looking at a different, at an inflation of the original setup. So I wire the things differently. And what happens if when I remove B1 here, I get this graph. And this graph has the property that A1 and C1, like they are still connected to beta 1, gamma 1, and here alpha 1, beta 2. But there is absolutely no arrows between these two graphs. I can basically move them on the page, and there will be absolutely no links going either way. And when I have like two islands, they will be independent by definition.
So why are you allowed to define your inflation like this? Like why beta 1 and beta 2 are not same?
Okay, so here what I say is that I will draw back the circle one, beta 1 and beta 2. By the way, if you have interesting questions like that, I'm happy to answer them and push the sum of squares to like just an introduction of 10 minutes, because this is important stuff. Like the sum of squares is a way to compute this faster. So let's really dig into this. Beta 1 and beta 2. So what I'm saying in the original model, I have a box that produces like every time I run the experiment, some value will come out to A and C. I have this box. What I assume is that if I have one device that behaves like that, I can also build another one using exactly the same components. So this is what I'm doing in this inflation. I'm having a device producing here beta 1. I have another device producing beta 2. They are built exactly in the same way, but of course they operate independently. It's like having two dice. They may be have the same number on them, and they will have the same weight. So when when I throw them, I get something with the same probability distribution. But if I roll 2 dice, they will not be correlated. So this is exactly the same spirit here. I don't know if that answers the question. Okay. Any other question on that stuff? So before we move on, I want to give you the reference to the paper that has this very nice example. I have so many notes here that I check. So it's 1609.00672. And what you do, you skip everything in the paper until you get to this example. Don't read. Seriously, don't read. Yeah, before I move to the next stuff, what I want to say is that here, we could eyeball stuff. I could say, okay, I take this triangle and then I move it like that, and oh, look. If I take this subgraph, I can say something and write constraints. The paper is very difficult to read because what they do is that they define a general formalism. If you have 1,000 variables, how do you identify the subgraph that are compatible with constraints? So you will have like injectable and pre-injectable sets. It's a very heavy terminology, but they did things properly so that you can take any scenario and derive if you follow their instruction. Yeah, but just read the example at first. It's very cool. Oh, I forgot to say one thing before we move to sum of squares. What I did here is just to connect sources and measurement in a sense in a different way in the inflation. Remember this morning I said the difference between classical and quantum is that classical information I can clone it, and quantum information I can't clone. The thing here, I use exactly the wires and the connection in the same way. I did not suddenly say, oh, by the way, here you have alpha 1, but I'm also using alpha 1 to connect a different copy of C. But this is, if I have classical information, this is something I'm totally allowed to do. Take the original locally done variable and add connection and broadcast them to more parties. And that's what distinguishes quantum and classical in the inflation setup. If you just do things like I've done here, where you don't make copies on the wires themselves, you will characterize sets that characterize when those variables are classical and when those variables represent quantum sources. So if our original goal was to distinguish classical and quantum, so if we just use that inflation, we will fail at this goal, because everything that's compatible with this quantum mechanically will also be compatible. Like if I don't see a difference, if I see that it's compatible either with quantum or classical and use only this technique, there will be no difference between the two sets. I don't know if that's very well explained, the difference between classical and quantum in the paper I mentioned. I think it's only about classical things, and they have a paragraph at the end mentioning that. We will have very soon papers about how to apply the inflation in the quantum case. Those papers will come in the next month or 2 months. So basically all that talk was to prepare you for like this series of stuff coming up. And it's very fresh. So if you start working on that, you will be like among the first people in the world to explore the topic, which is quite cool. If there are no remaining questions, then we'll move to sum of squares. Erase some of the stuff that will give you a bit of breathing room. I will send you the number if you need not write it. And I guess Gibran, we have like what, 25, 20 minutes?
Yeah, 25.
25, cool. And I think, okay, in terms of contrast, this starts to be very busy, but it's probably clearer for everybody in the room that you can use the very left one. So I'll start on the middle. I will start to remind you something that Emin talked about. if we have a state, psi, and we have a measurement m, so remember like a measurement was a collection of measurement operators such that we have mi dagger mi sum to the identity, then the probability of getting I, we contracted the states twice, bra and cat, with this in the middle, and we get the probability of the result. I will do a few things to like adapt this notation to what I'm going to do later. The first observation I'm going to make is that, let's say now that we do a measurement on two states. Like let's say we have a subsystem of phi here and psi there. And we do the measurement mi on this one, and let's say nj on the one on the right. So what's the probability of getting some answer ij? I'm going to put the state phi and psi on the right, phi and psi. And now I'm going to have mi dagger m, nj dagger n, and so on. So here I assume that the states were product states. There was like a state for the subsystem on the left and a state for the subsystem on the right. But what's interesting in quantum physics is when you have entangled states. So there would be states that are shared by both subsystems. So the only thing that changes here is that instead of having a state for every of the system, I will have a global state that's shared by all the devices. So the situation I'm thinking of is, for example, the one where I have a laser here, and it shines on a crystal, and then you send 2 photons to measurement devices. And here you give instruction about like what you want to measure. And then you will get an outcome for the measurements. Okay, let's use I and J. Basically, X and Y will select which measurements you do. And what you have there, here, is your state mu. That's the setup I'm considering. Don't worry about like, if you're not very familiar about the quantum formalism, I'm not going to use like any of it, like most of it. I'm just going to use the algebra of those things and try to find limits on what correlations can do. This is what sum of squares is about. I will erase that in the middle and keep the setup over there. So I will adapt 2 things. Yeah? Yeah? You mean?
I did not see some of the terms.
In the middle that I just erased?
Yeah, the one, the probability of I.
Oh, okay. So I'm going to state them. I think we have some glare from the, I should write it bigger. Let me write it on the left, so I have more contrast here. Crap. Let me use a pen that has a larger. Nice. Is it clear for everybody here? So I put my state, I put the measurement that I do on the left device, I put the measurement that I do on the device on the right, and I put my state again, and that will be exactly what I need to write to see what measurement do I do on 2 particles using 2 devices. You mean? Oh, yes, thank you. Now, to make things interesting, because if I just have, we've seen earlier today, right? If I just have one variable going to 2 boxes, like this, then I can basically do everything with that. So it's not interesting in quantum mechanics to study just I and J outputs, because I will not see a difference because with classical I can already do everything, so I will not gain anything there. So what I'm going to say, and I put that on the drawing here, that I can choose in both boxes which measurement do I do. So it means that both my measurements here, they have indices X and Y that select between different measurements that I can perform. But as you see, like, I'm always going to have those measurement operators appearing with their adjoints. So now I will redefine this, and I say this is equal to A X J, and this is I. and this is equal to bjy, there and there.
By x and y, you mean different observables?
I mean an index. So, to be clear, if I start with this, I have a collection for every x, I have a collection mxy. So that was what Amy put, but now I do that for yeah, perfect. I have that for every y, such that the sum over I of mi, but this one takes an adjoint, is equal to the identity. For example, let's say, in our case, we only need two measurements, 0 and 1. And the same for n. But because only these products appear, then I don't need to be very, very so precise. I can just group them in that mega operator. And of course, what I get on this A is that the sum over I of AIX is the identity, and the sum over B of ABJI is the identity. And I remove that. Actually, there is even more things that I can do with those new variables. First of all, AIX, I leave that to you to check later, but the way it's defined, this one is equal to its own adjoint. And the same for BJY. It's equal to its own adjoint. And of course, other condition that I have, that those operators, whatever state I put alone, because they come from a product like this, they will be non-negative. And the same for Bob, the measurement on the other system. So these are like conditions, more conditions. And the last thing that I'm going to say is that I'm assuming that I'm doing measurements like the AIX, wait, no, the I is below. AIX is down there, and the BYJ is down here. Those measurements are not joint measurements. They are done on different parts of a quantum system. So what I will have is that AIX BJY is equal to BJY AIX. That's the thing. So now we have a description of an experiment that we can do. And the way people distinguish what's classical and quantum in the case of having just two observers and one common resource, this system, they can be characterized by linear inequalities. And those inequalities, they are called Bell inequalities. So remember, I push a little bit the SOS, so this will be like a bit compressed. Who has heard of Bell inequalities in the room? Okay. So I will give you one. It's like the first like real modern Bell inequality without extra assumption that has been discovered and tested experimentally. It's called the CHSH inequality. And there is a nice review. I'm not going to my notes just to save time, but it's Nicolas Brunner et al. I think it's 2014. It's called Bell non-locality. And you have like more details about well, all these inequalities are derived and how they work. But I will look at them for the sum of squares postpose. I will look at them more from an abstract perspective. How do we find limits on those things? So the inequality I'm going to consider, I will put like I. It's what I obtain when I do measurement in the following way. A sum over AB, and I take the, wait a minute, IJ, because I'm using IJ for the outputs. And I'm looking at AX equals 0, I, BJ, Y equals 0, plus AI, X equals 0, Y equal 1, plus, and I'll tell you in a minute like what this corresponds to. X equal 1, BJ, Y equals 0, minus A1, j, x equal 1, y equal 1. So this I is just a polynomial in those operators. And what I can do with this polynomial is just evaluate it using the state mu. And now I will define what it means to evaluate something. It's just doing this contraction with the bra and the cat corresponding to the states. Okay, one thing that we moved from evaluating just a product of operators, just one of them, we moved to polynomials. But the great thing is that everything that we do here corresponds to an algebra. In particular, it's a vector space. So if I take linear combination of things like I've done here, I can still compute that value. And I want you to observe that like this expectation value of I corresponds to measurement that I can actually do. I can measure AI bj for settings 0, 0. I can measure for settings 0, 1. I can measure for 1, 0. I can measure for x 1, 1. So now, if I just have probabilities of ij given xy, I can relate it to this value here. What I'm just going to do is this. I just sum over ij, because this is what I have here. And wait a minute. Here I have a small correction. This is a plus, because I and j, they are measurement, they are bits, 0, 1. And the variable a and b, they actually measurement operators. So this should be 0, 1. So here I have I plus j. And basically, so I need to put pij 0, 0. So it's going to be like the output ij given xy plus pij 0, 1 plus pij 1, 0 plus minus pij 1, 1. So this is the way I'm going to relate the observation to the value of like what I do with this algebra of operators. Give me a minute, I need to erase that, and then I'll show you like how summer scale work. What I will do actually for sum of squares is I decide to only work with expectation values of polynomials of the form f something. And now what I will do is I will translate all the constraints that I wrote on the leftmost part of the board. I will translate those constraints on expectation values, because the idea is then I will write an optimization problem that contains only expectation values, whether it's a thing of things that I can actually measure or things that I just make up and I can't observe, but values that I could compute in principle. And I will translate like all these constraints. So the first thing that we are going to observe is that if I just have 1 inside, this is mu. By normalization of states, it's 1. Now, if I take if I take anything that has a, I, x, b, j, y, whatever comes before or after, and wait a minute, so in every relation that I put, f and g are polynomials in the variable a, I, x, b, j, y. So formally, inside a non-commutative polynomial ring. And I have a paper, so you can look at my archive. I call it about SIMD poly, but I define, look at my archive, this reference there defines this more formally. Here we just play with the symbol. So f and g as this polynomial. Every time I have something, and I have this in the middle, I can say the same thing as if I commute A and B. no, I'm writing this relation in terms of expectation values, but it actually comes from a relation that I had purely on operators. And now I know also that if I have f and g, and I have a sum over I of a, I, x, so this, by linearity, I can take the sum out. It's exactly the same as summing over that. But I know that this is actually the identity. So this is equal to just the expectation value of fg. One thing you remark, I had said that in my definition, it depends on the state. I'm just being a bit lazy. I forget to put the mu, but you have to think it's there. What other constraint do I have? The Hermitian thing, every time you have something, you can replace by the Hermitian adjoint. So what we are going to do is always write without the adjoint. Simplify the notation. This you actually don't need. Oh, there was something that I forgot to put on this board. They sum to identity, and they are projective measurements. So it's something that Amy did not explain. I will assume that it's there. It's going to be in the textbook. Is that if I have, let's say, A0x product A1x, this is equal to 0 because it means that I'm asking the overlap between two different outcomes of the same measurements. So projective measurements, so the overlap is always 0. It's like two projectors that project on a different subspace. I get something that's equal to 0 after that. And if I have AIX, and I take the square, it's a projector as well, so it remains the same. These are like the additional conditions. So I enumerate those additional things. Here I do them for the first subsystem A, but the similar thing will work also for the subsystem B. So if I have AIX, AIX, I can just replace everything by just one copy of AI. And now if I have FAIX, FAI prime X, G and I is not equal to I prime, then this is equal to 0. So what I will do now is I will add one condition that's the key one, and then we will use that to build an optimization problem. And at every step in the optimization problem, we will write expectation values, and we will use those rules to simplify them. So the condition in one is called sum of squares. It comes from the following observation. If I have any f, and I take f dagger f, in classical optimization, if things were not quantum, I would just put a square, f square. But no, those things are quantum, so they don't commute necessarily. In particular, when I write f dagger f, it means that I will reverse the operators in f dagger, because the adjoint reverse the operator. Then, of course, we said that every operator is equal to its own adjoint, but you must not want to forget to reverse them. So the thing is, this is equal to the expectation value of mu on f dagger f mu, but it's actually equal to f mu dagger, so that's now phi, and f dagger mu, it's now phi. So that thing is always non-negative. So that's the condition I'm going to put. If I multiply something by its adjoint, whatever polynomial it is, the result is going to be non-negative. Gibran, how many minutes I have remaining? 8. That's okay. That's good enough to give a test. So now the thing is, I'm not going to prove it. It's actually the difficult part. I don't even know how to do it. I use these tools. The thing is, if you can write those conditions just purely on expectation values, you forget about the operators. And you can write all of that, and you can solve it, then you actually characterize exactly the set of quantum correlation. I put a Q for the correlation. So now, how would you solve the problem in practice? You say, I want to maximize. So actually, what's the goal here? I forget to say what's the goal. The goal is, we have this inequality CHSH, and we want to say, what's the maximum value we can obtain using quantum measurement and quantum states. So what you say, okay, I don't know how to optimize over operators. Okay, maybe I know how to optimize if I fix the state to be qubit-qubit. then I can parameterize and I solve, but you can't solve for every dimension. What we are going to do instead is just to use these expectation values, and when I write them as kind of symbols, and I relate them, they become variables on their own, but they don't refer anymore to the dimension of the quantum system. I just write a variable for every of the things in brackets, just a scalar. I relate them, and I can obtain an answer. So if you could write those constraints for every polynomial ever, you would solve the problem. You would get the exact value. The problem is that we have infinitely many polynomials, and that we can write because we did not put a bound on the degree. So what I'm going to do now is to say that the degree of anything, put this in quote marks, is bounded by D. So what I'm going to do is I'm going to work with the space of polynomials of degree at most, let's say 2. And I will spend some time looking at this particular constraint there, the F dagger F, because that's the one that gives a name to the technique. So now I'm running out of time. I have like 5 minutes remaining, and I'm running out of space, but I think I can manage at least the space problem by erasing what's on this board. Stop me if there is something crucial there. Otherwise, we have the translation on the right here. If we need more time, I'll take over the session tomorrow and just restart this part, but I take it 5 minutes. It's enough to give a list. So the first thing is that I'm looking at this condition there. But now I say that the degree of everything was less or equal than 2. So I will say that the degree of F is less or equal than 1. So observation, every polynomial of degree 1 in those variables, and remember we had x equals 0, 1, y equals 0, 1, I equals 0, 1, and j equals 0, 1. Every polynomial in this variable can be written in the following form. Alpha 0 a, what do I put here? 0x equals 0, plus alpha 1 a x equal 1. And maybe you disagree with me, actually, because there is something I'm forgetting here. No, wait a minute, stack. And I gave you a hint because I only put I equals 0 and j equals 0. So what's happening? The trick is, remember, we have a0x plus a1x equal identity. So now every time I need to use actually a1x, I can just use this instead. And in particular, if I want to use a1x, I just can use the identity here, like it's hidden, it's a scalar, and any of those, and I can write my polynomial. So now in the few minutes that remain, I will show you how to write these constraints. So the thing is, now I will write f in a slightly different way. I have the coefficient gamma, I have the coefficient alpha 0, alpha 1, beta 0, beta 1. I will put a dagger here, and I put operators in the middle. A0, 0, A0, 1, B0, 0, B0, 1. That's exactly the same thing. And now if I write, okay, wait a minute, no, I put the dagger on the right because it's nicer for the product that I want to do. If I write now f dagger f, I have, okay, wait a minute, if I want to do this, nope, this way, sorry. Gamma, 0, alpha 1, beta 0, beta 1. Tac. F dagger F now is going to be my thing over there. Operators in the middle. And now, same thing here. Operators there. And finally, my variables again on the right. And now I can go directly for my punchline. I will use the blue color to do the last step of this thing, just to save a bit of time. Now I'm going to look at the expectation value of that thing. The thing is, those two vectors on the right, they don't have any quantum variables, they're just scalars. So when I compute the expectation value, I can just compute the expectation value of the thing in the center. So here I'm going to zoom on that. I'm going to zoom on this, I'm reusing that. How much time do I have? 2 minutes? Or now?
Sure, 2 minutes.
I don't have my clock, so okay. Okay, so in the middle, this is a matrix of operators. And I have my vector of scalars on the right here and on the left. So what happens is that this is a matrix that I'm going to call X that is composed fully of expectation values of things. And then the condition that I impose is that for all polynomials of that type, so for all vectors here, because those vectors fully parameterize the space of polynomial of degree 1, this overall thing is non-negative. So it's the same condition as saying that V X is non-negative in this way for all vector V. And this is the same as saying the matrix S is SDP. That's how you map the quantum problem to a sum of squares, like a moment-based relaxation. I think I should cut it there because otherwise we don't have a break, right? Let me check if I'm... No, 1 minute overrun. Oof, I'm being polite. What I suggest is that we don't take many questions now. I'll reboot tomorrow at the session. I'll redo the last step of this example again, maybe on the computer, and then you can ask as many questions as you'd like, if that's okay for you. If there is like a burning thing, I made a mistake with the notation and so on, I'll take it right now. Otherwise, I'll just push it to the session tomorrow. Is that okay?
Thank you very much.